Parent functions and transformations. So in math, when you have a relationship between two variables, that's called a function. So one of the variables is our input, and typically that's x. One of them is our output, and typically that's y. But when we talk about it in terms of function, sometimes we use f of x instead. And I'll write that just so you can see. So y equals x would be a very, or we can use function notation for the output and say f of x, which just stands in for y, or the output, equals x. In your notes packet, look at that first exploration. It says work with a partner, and you can pause the video in a moment and do that, or you can do this on your own. So this is just an explore to see what you know before we get into the actual notes. So below are graphs of 8 basic parent functions. And a parent function is the most basic type of function or relationship, a certain type of math relationship between an input and an output. So see if you can classify each function as, and then here are all the types that you see graphed below. A constant function, a linear, an absolute value, a quadratic, a square root, a cubic, a reciprocal, and an exponential. Some of these you have worked with in Algebra 1, and some of them you haven't. So pause the video now and do your best to match them. You don't have to write down a justification for your reasoning, but as you're doing that, make sure you have some kind of reasoning in your mind as to why you think the graph matches with that type of function. All right, see how you did with matching the names of those functions with their graphs. So in this section, we're going to focus on 4 of these. So we're going to focus in on the parent, or the most basic function, of a constant function. So you can see that that is just a straight line that goes through a value of y. So in this case, it's 1. So y, or f of x, equals 1. Very simple function. We're also going to look at a linear function, absolute value, and quadratic. And then later on in Algebra 2, we will cover the other functions that you see. Now look at the graphic on your notes that shows these 4 basic functions that I just mentioned. So functions that belong to the same family, they share key characteristics. The parent functions is the most basic function in a family. Functions in the same family are transformations of their parent function, which I will get into. First of all, let's just review what a definition of a function is in math. So it's a relationship between two variables, an input and an output. What makes it a function is that for each input, there's only one output. The other thing is that we will learn or use function notation. And so you will see that f parentheses x in place of the output as y. So what that stands for is the function in terms of x. We usually don't say that, though. That's kind of a long phrase. So we simplify it and we simply read that as f of x. Or if a different variable was used like g, we would read it as g of x. Now I want you to look at the picture of each of those basic functions. So with a constant function, we just use the basic number of 1. But notice that the output is just the same value there. And then it is, when graphed, it's a horizontal line, because all the y's, or the outputs, stay on the same value. Linear, it's f of x equals x. And so you can see, if you were to graph this, a set of points, we'd go over 1 and up 1, because x and y are the same. Here, the x and y would be 0, 0. Here they would be negative 1, 1. So it's a line with a positive slope that rises from the left to the right. It also goes through the origin, and that is a key feature of many, or actually 3 of the 4 functions that we're looking at in this section. Absolute value means the distance, or another way to think of it, we always express distance in the positive value of your input. So if we input a 1, then our output will be the value of that, which is 1. If we input a negative 1, the value of that would, or distance, would be positive 1. Thus, we get a V-shaped graph, and notice that it also passes through the origin. Finally, the quadratic. So when you square, what happens is it bends the line. It bends the graph, so now we have a curve. It also goes through the origin. And then for your input, to get your points, so if we put in 0 for x, we square it and get 0. If we put in 1 for x and square it, we're going to get 1. Same thing with -1. If we were to put in 2 and square it, we would get 4. So that's why this graph increases this way. When we talk about functions, we talk about the set of values for their inputs and their outputs. The name for that, the set of values of their inputs, would be the domain. These would be all the values that would give you real numbers. So you can see all the domains for each of these functions. So all real numbers, you can have anything for the input in a constant function. Same thing for a linear function. So if you think about y equals x, you can plug in any real number and get a real number output for this. Same thing for absolute value and for the quadratic function. Now when we talk about the set of resulting outputs, that is our range. So in the case of the constant function f of x equals 1, the only output that we have, y value, is 1. With the linear function, we can have a full range of outputs. With an absolute function, notice that the y values stay up in the positive. So they can also equal 0, but our possible outputs are greater than or equal to 0. And the same with a parent function of the quadratic, that our resulting y values will be up in the positive because of the nature of this equation. So domain is our set of possible inputs that'll give us a real number output. Our range is our set of resulting outputs. Now let's get some basic notes down about transformations of functions. So a transformation just means a change. And then we talk in math specifically about different types of transformations. Some of these are going to be familiar to you. And then as I talk through those, you'll probably want to pause the video so that you can get down the notes that I have for each of the type of transformation. So I place those 4 parent functions over to the right just as a reminder of the ones that we're talking about. When we start putting different values in, multiplying by x or by the absolute value of x or x squared or adding or subtracting, then it shifts that graph of each of those functions, and they're no longer the parent function. So a translation, this is when the graph shifts horizontally or vertically. There's no shape or orientation change. We're going to talk more specifically a little later on in the notes and the next section of notes about where those values are exactly in the equation. But right now I just want you to know in general, when we say a translation, it simply means that the graph of the function will either scoot left or right or up or down. There's no shape or orientation change. Now when we have a reflection, this is when your original function, once it's reflected, it flips over a line of reflection. And so very common reflections that we'll work with are ones that are reflected or flipped over the y-axis or the x-axis. Another type of shape or transformation of a function can be a vertical shrink or stretch. Sometimes shrinks are called compressions. So this is when, as you look at the graph, from the original to the transformed one, the graph flattens. And the way that you do that in the equation is that you multiply the entire output, everything that f of x or y equals, it's multiplied by a factor. And the factor needs to be less than 1, but greater than 0. For example, 1/2 or 3/4. Now a vertical stretch is when the graph appears to narrow, or if it's a line, then it becomes steeper. And this is when the entire output is multiplied by a factor greater than 1, so 2, 3, or 4. We can also have horizontal shrink and stretches, or again, another word for shrink is a compress. These are difficult to determine by the shape of the graph, so I don't even describe that to you. But what you can tell from the equation is that the input only, so the x value only, is multiplied by the factor. All right, so on number 1, we're going to graph g of x equals x minus 4 and its parent function. So I've started and I've graphed the parent function. So do that now on your graph. We can see that g of x equals x minus 4, that if we were to take away the x minus 4, we would just have a linear function. So I wrote down that the parent function, and I just called it f of x, equals x. And I know just from earlier in the notes that it passes through the origin and that the input equals the output. So I graphed the points 5, 5 and negative 5, 5. When you graph in this class, always make sure that you draw and label an XY axis and label your scale. So now we're going to graph the transformation. So that is g of x equals x minus 4. I'm going to place it right here in my table. I want to see what this graph is doing in the negatives, at 0, and in the positives. So if I plug in negative 5, subtract 4 more, I get negative 9. At 0, I get negative 4, and at 5, I get 1. So I'm going to graph that, negative 5, negative 9, 0, negative 4, 5, 1. Now you can see that our slope is still the same, and you can tell that also by the equation. Here we have a slope of 1, and in the parent function we do as well. So I've got a line that is parallel, and you can see that it's been shifted down 4. 1, 2, 3, 4. If you look at the equation, notice that 4 has been subtracted. So we can draw just a general conclusion that if you subtract a value from the end of the input, that's going to shift the graph down. Now, what do you think would happen if g of x were x plus 4? Well, I bet you can imagine it's going to shift 4 up. So to describe this transformation, we would say that this is a vertical translation, not stretch. Let's see if I can write that. This is a vertical translation for down. And I'm talking about the function that we graphed of g of x equals x minus 4. Now look at number 2. I'm just going to have you explore what happens when we multiply the output by a negative. So it says graph p of x equals negative x squared and its parent function. So I started with the parent function, and that's graphed in red. I noticed in the equation that this was a quadratic, so I knew that my parent function was going to be f of x equals x squared. So just using what I know, that it's going to pass through the origin and be at the points 1, 1, and negative 1, 1. So if we can plug some values in, let's see what is happening to the graph in the negatives. So we'll do negative 2, negative 1, 0, and in the positives. So I'm plugging it into this equation. If I square negative 2, I get positive 4, but then I still have that negative I need to multiply by. If I square negative 1, I get positive 1, but I have the negative. Square 0, I get 0. Square 1, I get positive 1, but then I need to multiply it by the negative. And then finally, squaring 2 is 4, but I need to multiply it by that negative. So notice then, as we graph these, that our graph has reflected. So I've got the points negative 2, negative 4, negative 1, 1, 0, 0. So thinking about the definitions of the different transformations, this is a reflection, and it's being reflected about the x-axis. So notice to do that in our p of x function, that our output, which was x squared of the parent, was multiplied by a -1. And so that causes all the values to become negative and the points to be reflected over the x-axis. On number 3, we're going to explore a couple more types of transformations. So we've got g of x equals 2 times the absolute value of x. I can tell just by that equation that my parent function is the absolute value, and I have that written in red. And I have it graphed in red as well, just going off of what I know from the parent function. So in my table, I have my transformed function placed. So 2 times the absolute value of x. I'd like to see what my graph is doing in the negatives. So we'll plug in -5, -1, 0, 1, and 5. So I just do the math here. I'm going to take the absolute value of 5, which is 5, times 2, which is 10. Absolute value of -1 is 1, times 2 is 2, 0, 2, and 5. So now if I graph those points, -5, 10, -1, 2, 0, 0, 1, 2, 5, 10. And then knowing that this is going to be a V-shaped graph, I can tell that my graph is skinnier. And so this is called a vertical stretch. Notice that the output was multiplied by a factor that was greater than 1. Now I bet you can anticipate what's going to happen with our parabola in the next one. So I've got the parent function graphed, and remember you can pause the video and kind of catch up with the graphing. And then we like to plug in our inputs, so negative, 0, and positive. Now we'll square -2, which is 4, but then we need to take a half of it. So that's going to be just half as big. Square -1, which is 1, but take a half of that, 0, a half, and then 2. So when we plot these points, look at what happens. So -2, 2, -1, a half. So this graph is flattening out compared to the parent. So this is what we call a vertical shrink. Sometimes you'll see it as a compression. Now it says predict what will happen with the graph g of x equals negative times the absolute value of x plus 5 minus 3. So I imagine that you are thinking of the parent function. So that's going to be our absolute value, since that's the math that you see in the function. And then you can start to see all the things that have changed. So we have a negative out front, so we're going to have an x-axis reflection. We have a value of 5 that has been added to the x. So when you have a value added or subtracted to the x, that's going to cause a translation left or right. So this is going to be a horizontal translation. Now if you were to put this on your graphing calculator, it would surprise you because it's actually going to shift the graph left. And then finally, this is just like our first one, that linear. We have a value that's being subtracted at the end, so this will be a vertical translation. So it's simply going to scoot the graph down 3. Now look at example 6, and this is the last one that we're going to do on this video. So the table shows the height y of a dirt bike x seconds after jumping off of a ramp. What type of function can you use to model the data? Estimate the height after 1.75 seconds. Well, you're the master of your graph, and so am I. So I noticed that my y values spanned from 0 to 30, so I established that scale on the left, and that my time went from 0 to 2. So I established that scale on the right. I don't have any negative values, so I don't have any negative portion of my graph. So now when I plot this, my time at 0 seconds is about 8. I'm going to switch colors to blue. At a half a second, I'm at 20. At 1, I'm at 34. No, I'm at 24, sorry. That would be high. At 1.5, I'm at 20. And then at 2, I am back at 8. Now, when you're graphing a set of points, you ask yourself, does it make sense to connect the lines? So in this situation, was the situation at all the heights in between at these as time went on? And yes, because this is a dirt bike going through the air. So as best that I can, and you can on your graph, you're going to want to connect these in a nice smooth curve. Now, can you think of what parent function that looks like? And I bet you're saying it's a quadratic, although the quadratic has been reflected. Now, if we estimate, at what our height will be at 1.75, so that's going to be right in between. So it looks like we're going to be at a height of 14, perhaps 15. So 1.75. That's how I could write that. So this is just an example of a real life situation, and using one of those functions that we learned in this section to model it. Again, when we make the decision whether to connect our data points or not, we think about, are the values continuous in this situation? Oops. All right, that's all for these notes.